Welcome everybody to our first MathWorks mini-series session of the year. We're really excited to be kicking off this annual webinar series that we do here at RoboNation. If you don't know and you've just stumbled upon this video who RoboNation is, we're a 501c3 nonprofit based out of the US, but we offer 9 educational robotics programs spanning from the K-12 space all the way up to university and postgraduate. In those robotics programs, we have remotely operated vehicles for underwater. We've got autonomous vehicles for on the ground, in the air, in the water, under the water. We've got just about everything here at RoboNation. And we're excited to welcome you to this community, a really awesome group of fanatics and students and educators, industry experts, etc. alike. But we've got one of those folks here who's been a longtime member of the RoboNation community. His name is Abhishek Shankar. He works with MathWorks, one of our longtime sponsors here. They're a software company that creates MATLAB and Simulink and all the things that many of you probably use to make your robots work. But a fun fact about Abhishek is that he actually was an IGVC student. So he's participated in our events. He understands what it's like to build a machine from scratch, make it work autonomously, and understands the ins and outs of robotics. We're excited to kind of kick off this series with a session about filters to reduce sensor noise through MATLAB. I'll let Abhishek take over most of it, but just for the topic recap, you may have read it in the emails, but all sensors are noisy with filters. You have an effective tool to mitigate them. So in this webinar, you're going to learn how to stream sensor data to MATLAB, analyze the noise, and effectively filter them by designing your own. So we're very excited to welcome Abhishek. Like I said, please join us as we give him a warm welcome to our first session of the year.
Thank you, Alicia. And welcome everyone. I'm glad to kick off our first webinar of the 3-part webinar series that we're doing with the RoboNation. Like she said, I'm a previous IGVC student, so I know how it is like to be in a competition and having things go wrong, sensors being like noisy and wacky, and having to work through all of that. So in this webinar, I want to talk about how you can design filters to reduce noise in your sensor. If you're using, for example, an IMU for your navigation and like estimation for orientation, you might have seen that it tends to drift over time. So if you have your robot running for about say 2-3 minutes, then you know that your error in your localization accumulates because you're integrating IMU or the acceleration from your IMU to get your velocity and position, but then that error in the integration adds up over time. In this webinar, I want to talk about how you can kind of reduce that error. You can't fully mitigate them because sensors inherently are noisy, so you can take away all the sensors, but there are some filters that you can design to at least minimize it and mitigate the effect that it has on your robot localization. So I'm going to be focusing on 3 things today. The first one is collecting data with MATLAB. Again, to analyze and design your filters, you first need data. You need to see where things are going wrong, where things are being noisy. So it always helps to have some data in your system to analyze. And then the analysis can be done in time domain or frequency domain. I'm going to be focusing on frequency domain because that is the most common and often most useful domain to look at. So you can see where the errors are, what frequency the noise is at, and then how you can like design filters to reduce that noise. So for the first part, I'm going to be looking at how you can stream sensor data with MATLAB. For this one, I'm using an Arduino, so you do need an Arduino support package for MATLAB. So this is a free add-on that you can just go to the add-ons page in MATLAB and download it. I'll show you where it is located once I switch to the MATLAB screen. But if you know where the add-ons tab is, then you can just click on it and then search for Arduino support package. And you'll see 2 of them, one for MATLAB and one for Simulink. And depending on what software you're using, you can install either or both of them. So we are going to be streaming sensor data from the MPU 6050 IMU. It is a 6-axis IMU that has acceleration and angular velocity. And it is being sampled at 150 Hertz. I think the maximum sample rate is 200, but I'm going to be holding it at 150 hertz just so we can get all the data and see it. And the next part that I'm going to do is analyze the noise present by converting into frequency domain. In MATLAB, you have a neat function called FFT that would just convert your signal into frequency domain and then plot all the frequency present in your system. So this is super useful when you're designing filters because a lot of times you want to cut off values above or below a certain frequency, or you just want to let values between a certain frequency to pass through because you know the rest of them is noise. Again, I'll go over how you determine which one is noise, which one is your signal, and then we'll see how to filter them using the filter designer live task, which is a live task in your script that you can just click and add, and that would let you to allow that would allow you to filter your signal and design the filter based on all the parameters that you decide when you look at the frequency domain of your signal. So enough of presentation. Let me switch to MATLAB. Yeah, so before I go into the script itself, like I said, I want to show you how you can install the add-on. So if you see over here, there's an add-ons tab. Just click on it, and then that should open the tab. Pull that up. And then you can just click on the search tab and then search for Arduino support package. So you can see there are two MATLAB support package for Arduino and then Simulink support package for Arduino. I'm going to be using MATLAB for this webinar, so I'm just going to install that. Well, I have already installed it, but then if you don't have it installed, instead of manage, you'll have an option to download and install over here. So this is how you install the support package. It's super easy. It is free. You just have to go to the add-ons page, search for it, and then hit install. So with that installed, you can read sensor data, like you can read data from your Arduino, you can connect to it, you can access the I2C and the other communication protocols to read data. So for this webinar, I have the MPU 6050 connected to the Arduino, and then the Arduino is connected to my laptop. So I'm gonna see if I can pull this up without breaking any of it. So this is the Arduino, and then this is the IMU that is connected. I'm going to put it back because I'm scared that some of them will come out, and then I don't want to do it again. It's a little flimsy setup right now, but it gets the job done. You can read the sensor data from the sensor, and um, and then you can stream it to MATLAB and plot the data um, in your screen. So what I'm going to do first is define the sample rate for my sensor. So like I mentioned, I'm going to be sampling it at 150 hertz. And then we go to the library task, and then I'm going to define the Arduino and then the IMU. So again, to define the Arduino, you just call Arduino, and then for the IMU, there's the MATLAB function called MPU 6050, if that is the IMU you're using. There's also MPU 9050 thing, which is a 9-axis IMU with the magnetometer data too. So that is also supported um, in the support package. So you search for MPU 6050, and then you pass in the Arduino handle. You're going to set the sample rate to what we defined over here, and then we're going to read 150 samples per read cycle. So um, it would take 1 second of data every time you read. So I'm going to run this section, which would define the Arduino and the IMU. Yeah. Here you can see the IMU is defined with all these parameters that we just passed in. And the interface is I2C, that is the default interface. And then it's going to take the default address for the MPU 6050, which happens to be 0x60. So once that is defined, you can go ahead and collect data and plot it from the IMU. So what I'm going to use here is something called an animated line, which would animate the sensor data as it's reading it. And then I'm also going to be saving it in this variable data. I'm going to be collecting 1500 samples. So since a sampling rate is 150 samples per second, this is about 10 seconds of data, which is pretty good for our purposes. That is enough to analyze and design our filters. So let me run this section. I'm going to move the sensor around so that you can see the values. Oh, huh. This is not ideal. It is being plotted in a different 3D plot, actually. So let me clear this one. Then I'm gonna define a new figure. Um, Use that to plot it again. Hopefully that fixes that issue. On that figure. Okay, let's run that again. Yeah, that is better. So now you can see all the values, X, Y, and Z acceleration values. So that's what I'm plotting right now. So I'm just taking the acceleration values from the sensor reading. And then, so yeah, you can see all the data that's being read, and the colors determine what axis it is. So I have the red um, for X, green for Y, and then blue for the Z axis. So you can see the Z axis is around 10, which is what the acceleration of gravity is, which is 9.8. And you can see that there is noise in the system because you can see all that wiggly lines when you're going. It's not smooth. It is changing. Some of that is actual signal, and then a lot of that is just high frequency noise in your system, which is inherent to most sensors. That is how you would stream it. Again, I'm using the animated line, which is animating the plot. So if you um, see here, you can zoom in to like certain sections and see how like all the data points are like going up and down because there's been a lot of high frequency noise in the system. But from this, I can say that there is high frequency noise in just by looking at the time domain. But then I can't really say what is the frequency, like where the noise is coming from. So I can just do like a generic assumption that this looks like high frequency noise. So what we're going to do next is add noise to the data. So this is already a little noisy, so I'm going to add more noise. This is because a lot of times your IMUs are mounted in your robot between like motors or between propellers. So for example, if you're using it in RoboSub, your sub can have anywhere between 4 to 8 propellers. So that is a lot of spinning things in your system. So that's gonna add like frequency, that's gonna add like noise at that frequency where what it's spinning at to your robot. So what you're gonna see when you have that when you have that sensor in the robot is gonna look vastly different from what I have here because you're gonna have all the noise from the motors and the propellers running around added to your already noisy signal. So that just is gonna make it even more worse. So for to simulate that, I don't have a huge robot, sadly. So I'm gonna be adding a sine wave that kind of mimics the motor noise. I'm going to be having something at 25 hertz, which is approximately 1500 RPM. But then if your propeller runs at a higher or lower RPM, you're going to have frequency noise that is more similar to that frequency. In the frequency graph, when I go to the next part, you'll see the peak in a different value. Depending on what frequency your motors or your propellers are running. So let me run this section. It's gonna make that noisy data. So as you can see, the noise is just a sine function. And once I have the noisy data, I am gonna add it to I'm gonna plot both of them, and then we'll see how the FFT or the fast Fourier transform looks like for the data without the added noise, and then just the plain data. Let me run this section. Yeah. So before we look at the graph, I just want to quickly show you what the script does. Let me zoom in a little bit. See. Whoa. Okay, good enough. So what I'm doing is I'm taking the noisy data and then the actual data, and I'm setting the frequency to 150. That's the sampling frequency, and then you're going to do FFT of the data. So it's a pretty simple command. You just do FFT of your sensor data, and then I'm plotting it. So you can see the two plots. This is your data without any added noise. So even in this, you can see there are some noise over here. Um, and this is like a mirrored, this is mirrored along the middle because FFT by default gives you a mirrored picture. So what you're actually seeing, you can just focus on the first 75 hertz of this graph. So you can neglect the other half because it's just an exact copy of the first one. So you can see this, the highest peak is your actual sensor data, and then the rest is just noise. And then with noise, you can see an additional peak over here. So what I'm going to do um, is zoom in on that one. That's going to be at 25 hertz, which is, if you remember, which is where we added the noise. So our sine wave is 25 hertz. So it's saying that there is something at 25 hertz present in your signal. So let me go back. So again, if you have it, if you have the sensors collected, the sensor data collected from your robot, and then you do the same thing, you're going to see something similar, but you might see additional peaks depending on how many motors are running and then what frequency they're running on. And then that is also going to change according to time. So your motor is not going to be like constantly running at a particular RPM. So if you're changing directions or if you're um, accelerating or decelerating, there's going to be difference in the RPM of your motor. So that's going to shift this to the left or right, depending on if you're going slower or faster. Um, but you can safely assume that anything greater than let's say 5 hertz or 10 hertz is going to be noise because as you can see here, even with the plain data, anything greater than 10 hertz is just noise, and you can just filter that out. Which brings me to the exciting part of designing filters. So this is probably the most useful step, and designing filters is not that hard if you know what you're looking for. So in this case, we know that we want to design filters that will reduce all these values above, let's say, 10 hertz, right? So we know that is what we want, and that means we need to design something called a low pass filter. What that means is you're letting the low frequency signals pass through, but then you're stopping it at 10 hertz. So all the higher frequency is going to be attenuated or stopped, um, which works well for our system. But if your sensor has low frequency noise, you might want to look into high pass um, filter so that it stops all the low frequency and then lets the higher frequency go through. And you can also do something called a band pass, which tells your filter to let everything below a certain value out and greater a certain value out. So you only get the values between the range that you specify. So if you just want signal from 5 to 10 hertz, then you can do something like a band pass, which would remove everything else but that range that you specify. So I'm going to be using design filter live task, which is super useful. You can just go into insert in the tab over here, select on task, and then you can scroll down where there's a lot of apps. So I'm gonna search for filter. And then you can see that there's a design filter um, task, which is what this is. Oh, sorry. Yeah, this is what it is. So I'm gonna zoom out a little bit so you can see the whole thing. This is a simple app where it tells you, it gives you all the option for you to design your filter. If you click on this, you can see that you have an option to design different kinds of filter. So I have low pass IIR, but maybe let's start with a low pass FIR filter, and and then we're gonna choose a minimum order filter. So we don't want the order to like grow exponentially because that is hard to implement in hardware if you have like a really memory constrained hardware and you have like a huge filter, then it's going to take up a lot of resources. So I'm going to do minimum order. Um, and also, FIR is finite impulse response. I'm not going to go into the details of what a low pass and high pass filter is because I don't think we will have time to cover all the theory behind that. But then, if you look at the links in the description, you find some useful documentations that you can go through and like read up on all these different options because covering all of them would be a lot for this webinar. So I'm going to be focusing on a select sample of it. But you can go through all the options in our documentation. It is extensively documented. And you can also reach out to me through email, or you can ask me questions after the webinar, and I'll get back to you. If you reach out to me in email, I'll get back to you within like a day or two maximum. Um, so yeah, so I'm gonna go ahead and design a low pass filter with a minimum order. I'm gonna set the cutoff frequency to 10 hertz, and then, oops, I first have to change the stop band frequency. I'm gonna 13, and then this is gonna be 10. So I'll show you what the pass band and the stop band frequency is in the graph below. But I just want to quickly show you what is the design like workflow that you would go through. And then you can have some stop band attenuation decided. For me, 60 decibels works. And then I'm going to do like an equiripple algorithm. So you have like multiple algorithms. I'm going to go with equiripple. And here, if you see, this is what I meant when I said I would just explain pass band and stop band on the graph. So you can see that everything till 10 hertz is going to pass through the filter. So there's not going to be any attenuation. Um, the whatever signal is coming through is going to just pass through that filter. But then after you cross the 10 hertz point, it's going to drop off rapidly. And by 13 hertz, which is what we had specified here, it's going to drop off almost less than minus 60, which is what we mentioned here. So it's going to cut off rapidly, and this is what the pass band and the stop band frequencies are. And here you can also plot like different responses. So I have the magnitude and phase response given here. So you can see how the magnitude will change depending on the frequency, and then how the phase is going to change depending on frequency. And one quality of low pass filter is that it's going to be shifted in phase a little bit. Um, that is because it has to collect some samples to filter it and then give the output. So there's going to be some phase shift, but again, you can play around with it, try to minimize it, but a phase shift is inherent to a low pass filter. And in most robotics cases, that should not make a big difference. Um, Again, you can have, if the phase difference is huge, obviously, yeah, you're going to see a drop in your performance, but if it's small enough, then you probably wouldn't even notice it, and your all your navigation and your localization algorithms would do just fine with a small phase shift. And then I also have a whole zero plot. This shows that there are about 122 zeros, which shows that the order of your filter is 122. Now that is a huge filter. 122 is a lot of um, orders in your filter. So that means you're going to have to store 122 variables at least to do your filtering, which is which is a lot if you're using a small embedded device and you have memory constraints. So we'll look at how we can reduce it, but I just want to show you what the filter response would be for this filter. So I'm going to go to the next section and then, excuse me. So in the next section, I'm going to plot the filtered results. Go here, run the section. Yeah. Um, so you can see the filtered result here. You can see that there's still a lot of noise, but it is a little better than what we had before. It's filtering out all these random peaks that are coming in. So you're getting um, more signal than noise in the red one, which is the filtered signal. And if I zoom in over here to this part, um, so being finicky, but if you zoom in a little bit, you can see that there's still some peaks going up and down. Um, but for the most part, you're filtering out a lot of the noise that was present in the original signal, and you're not taking all the random peaks that come up because of these noise, and your signal looks a little bit more smoother. Um, but that said, there's still a lot of work to do. If you go below and then see the FFT results, you can see that the 25 hertz peak from our previous one, let me scroll up to show you that quickly. 25 hertz in the previous one is gone. So that noise has been filtered out from your signal. But there's still all these noise that could be filtered too. So what I'm going to do, um, I'm going to zoom in on that section. It's not letting me zoom for some reason. Oh, it's stuck at a different axis. But it's probably the same thing. So what I'm going to do is zoom in on this section over here. Oh, I think my PC is just a little slow. So bear with me over here. Um, the zoom of this one, messing it up a little bit. Go home, zoom. Yeah, there we go. So if I zoom in on this section, you can see that anything greater than like 3 or 4 hertz is probably just noise, right? Um, your actual signal is present in this range of like 0 to maybe 3 hertz. But anything more than that is clearly noise. So what we're going to do is go back up to a filter and then change it so that anything greater than, let's say, 3 hertz, and we're going to stop this at 5. So it's going to stop anything greater than 3 hertz from going through the filter. So let us wait for it to design that filter. But in the meantime, if there are any questions, do let us know in the chat, and I'll be happy to
Yeah, we've
answer
got
them.
two questions
Yeah,
so
sure.
far. The first one is by CMAC. He says,
Mhm.
we're using a BN0055 IMU and pressure sensor on our AUV, but getting noisy depth orientation data during dives. Would Kalman be better than moving average in our case?
Yes, for a lot of cases, Kalman filter is much better. If you're doing orientation estimate and like localization with your IMU, the BN055 is it? That's a I think that's a Bosch IMU. That is also supported in MATLAB, so you can resense the data on it and then design a Kalman filter. I have a short section after this part that shows how you can estimate orientation with the Kalman filter. And since you have a pressure sensor too, you can estimate depth and you can fuse both of them. But then going into details is that'll be a lot for this webinar. But what you could do is if you could send me an email if you're still having trouble fusing the sensor and like building a Kalman filter for those two, you can send me an email at Abshank. Actually, I'll type that in the chat so that you can reach out with your specific problem. Um, and I can take a look at it and we can help you figure out how to build a Kalman filter for that. Or if you have already built it, then how you can tune it and get it to work as you expect.
Awesome. Thank you, Abhishek. The second
Mhm.
question we have right now is from Sarthak. He said, hello, I wanted to ask how to get beta access to MATLAB Copilot.
You can, it's a little out of the scope for this webinar, but you can get the beta access for Copilot. I think it is out. If you go to like MATLAB pre-release, you can look at the 25A pre-release and download it. It should be pretty straightforward. I can show you in a window later once I'm done with the webinar if you're still having trouble, but it should be pretty easy to find. But also the 25A release is going to be in a month or so. So even if you can't install pre-release for some reason, you can definitely get the actual release itself, which should be much better and a lot of issues fixed with it. But if you still are having trouble getting, or if you really need Copilot or some AI, um, generative AI in your code, you can look up the AI Playground, MATLAB AI Playground, which is great. You can given it is also has an LLM running on it, so you can talk to what you want to build, and it will spit out the code that you can run in MATLAB. Um, I'm going to type that in the chat. I don't have the link currently, but if you just Google that, you should be able to see the uh, the AI chat playground. All right. Is that all, Alicia? Is there
Yeah,
any
those
other?
are all the questions right now.
Okay. Okay. So coming back to the filters, now that we changed the passband and the stopband frequency, again, you can see that it's going to stop everything after 3 hertz. But then that also increased the order a lot. So it's going to be 188 poles, zeros, which is a lot. But we'll look at optimizing your filter a little bit later. Excuse me. So let me run this again with the design filter. So one good thing is that the design filter, is going to be automatically updated every time you change something. So this line here makes sure that any changes you make is instantly reflected on your design filter variable. So you don't have to do anything else. You just change it and then you run this one and you can see how the data performs. Here, you can immediately see that the performance is much improved. Again, there is some phase difference, but I don't see anything major. So it's just a tiny bit. Um, Let me see if this would let me zoom in. If you zoom in here, the phase difference, if considering this is the peak, is about 0.1 second, which is not a lot. So you're getting a much better filtered response with a minimal phase difference. And if you go to the FFT, let me zoom in here, you can see that all the noise after 3 hertz is completely taken off. So you have a much more cleaner output from your IMU, which would reduce like the drifts and all that things that happen when you just use an IMU. But you can follow like pretty much the exact same workflow for any other filters too. If you have a hydrophone, or if you have a pressure sensor, or if you have anything else like a DVL, things like that, you can do the same thing and then get the filtered response to be used in your algorithm. All right. So we have this. It's pretty good, but the only issue, as I mentioned before, is that it has a lot of zeros, which means the order is huge. It's gonna have to save all these coefficients to run it on your hardware, which is not ideal. So let me try building a low-pass IIR filter, the same the same parameters that I had, so 3 and 5 for the passband and the stopband. And yeah, you can see the result looks, it's still stopping it at 3 hertz, and there's the phase response, but then you can see that the full zero plot is much better. So you just have 6 zeros. So the order went from 188 to 6, and you have almost identical performance. But then let's also look at the signal and see if there's like additional phase shift and how the filter performs. Yeah. So I think there's like a little bit more phase shift in this one, but you can see that for the most part, the filter is pretty good. So again, I'm going to zoom in to see what's the, uh, I zoom in. So again, from point one, it became point two, assuming this is the peak of the original signal, and then your peak is at around 2.6. So from 2.2 to 2.6, that's zero point 0.4 seconds. So it did increase considerably, but it is still less than half a second um, of your data, which for the most part would be fine. But then you can also fine tune it, play around with it a little bit to try and reduce this delay. But for this one, I'm going to be like, I'm okay with less than half a second of delay. So this design process is also kind of iterative, right? So you need to try different things. Your requirements might be different. You might have like a hard cutoff at the phase difference. You don't want as much phase difference. Um, so those are things that you'll have to play with, and then depending on your requirements, that would change. But over here in the filter designer app, you have all these different options that you can do. You can specify order too. I've choose minimum, but you can specify the order that you want your filter to be, and it would design the best filter it can for that order. And you can also like specify algorithms over here. For the IAR, you have like 4 different algorithms. I went with elliptic, but maybe you can go with a butterworth or something and see how that output would be. So again, this is like super easy. With the app, you don't have to like code like a whole butterworth filter or a whole elliptic filter. You could just select different things and it would do the work for you, get you the coefficients, get you the filter, and then you can simply just look at how your signal is going to perform for that filter. And you can also like display different filter response. So right now I have magnitude, phase, and full zero. Let's say I also want to have like a step response. So it would plot your step response in in the graph below, and you can choose like different things. You can click on filter information, and then it would give you like all the information of your filter. So that's how you can quickly design a filter with the filter designer app. Again, there is like a lot of options that you can go through in our documentation page. But I'm gonna not go through all of them because it would be a lot and I only have like about 15-20 minutes left. So I'm not gonna go all the way there because I do have other things to cover too. But yeah, if you have any questions, again, drop them in the chat. I'll address them a little bit later once we go to the next part, which is filtering live data. So now that you have the filter design, let's see how it would perform on like live data. So again, I'm going to be reading the sensor data. from the IMU.read function. The IMU was defined in our first step, uh, and we're going to be plotting that and see how it looks. Let me run this section. Oh, okay. I think it got the axis confused, so I'm gonna do picture of it. So when you have multiple plots, it's actually good practice to like define your figures so you know which plot is going to be used. So I'm going to run this again after defining my figure. Yeah. So now we can see the filter response. This is in real time. Uh, and even in the real time, even in real time filtering, you can see like there's a phase difference, right? Again, for my purposes, I'm okay with this difference, this little difference that we have in phase. But if if this is not good for you or you need like better phase response, you can always go back um your filter again over here and then just run it again. And it would give you the updated results. And this is super useful because a lot of time is spent on designing the filter. Implementation is pretty easy. Once you have the coefficients, you can implement it. But designing and trying it out is where you spend a lot of time. So you first design a filter. If you didn't have the app, you're gonna first do it in let's say Arduino or Python or even MATLAB, but without the app, you're gonna have to hand code your filter and then see what the output would look like. And then if it's not good, you're going to have to do like a completely different kind of filter and then see what that would look like. And then every time you tune something, you got to keep changing your code, running it again and again just to make sure you get the final filter like what you desire. But with the app, it makes it easier because it's just a bunch of button clicks so that you can focus on the high level aspects of your filter instead of worrying about, low level implementation errors or things like that, which is super important in competitions because I know that you won't have a lot of time to like play around and find proper filters. So having something like an app is super useful in doing that. So yeah, so that's how you design a low pass filter. In the last section, I just want to quickly show you um, how you can use the IMU filter that we have, which is a Kalman filter, as someone had asked in the question, to estimate orientation. So this is also used a lot, especially in sub or like GPS denied environment, indoors or RoboSub, where you heavily relying on an IMU and other sensors like pressure or DVL. So in this case, this one is going to give you orientation based on just your acceleration and your angular velocity. So let me, before I go over this one, let me run this to show you what it looks like. Oh, it was not able to clear the IMU, so I'm going to run it again. Yeah, so you can see that I'm actually moving the sensor and then it is correspondingly moving based on the filter that I have. So it is going to be moving up, down, left, right. So the x-axis is, the z-axis is down, so that's why it doesn't mimic the exact movement that I have. But this way you can like, well, I think one of the pins came out, so it can the I2C connection dropped off. But basically, you can see that when I move the sensor, it's going to calculate the orientation by fusing your acceleration and your gyroscope value or your angular velocity value. And to go into the code for that, it is again a pretty simple code. I'm going to zoom in. Well, my PC is a little slow responding to zoom. Um, But yeah, so you can see that I have the noise defined. Um, these have been taken directly from the data sheet for the MPU 6050. Uh, this is like of the manufacturing data sheet, so it is not going to be super accurate. It's going to be close, but you can always tune it to get a better response. But this is with the default noise values that are present and that you can get from any of your IMU's data sheet. So I've had the gyro noise and the accelerometer noise defined here. Then I'm going to use this IMU filter function, which is a filter based on an extended Kalman filter. Then I'm going to pass in the sample rate, the accelerometer noise, the gyroscope noise, and then the linear acceleration noise, which tells you what is the noise when you have like a linear acceleration. And this is like also taken from the data sheet. Once you have all of these, what I'm doing is the same thing. I'm going to be reading the IMU data. I'm taking the acceleration and the angular velocity values. So these are the last values that you see here. And then I'm going to use the iFilt, which I defined here, and then pass in the acceleration values and the angular velocity values to get the quaternion orientation. And then you can do something called a post plot, which is this thing over here. This would plot the pose of your robot or your IMU, and you can set the pose to the value that was filtered from your IMU filter. So for each sample, it is quickly filtering both your angular. It's quickly fusing both your angular and acceleration value to show the orientation. I'm gonna run this again, maybe a little bit slower. So that you can see. So again, the shakiness is because I was lifting it to show you. But for the most part, even with the default value, you get a decent estimate of orientation um, with the IMU filter. And again, this one right now, what I have is for a 6-axis IMU. You can do the same with a 9-axis IMU, which would give you a better result. Um, and you can also get like the noise for the magnetometer from the data sheet, but like all filters, you need to tune the noise values a little bit, um, and you can do that by like either passing through different values. So you have like a window, and then you're passing through each of the values in that window, and then seeing how the filter um, responds to that. So you can do like a simple for loop and then have the filter respond to different noise values within a particular window. Or you can also do like a stochastic method where you're sure that the noise value is going to be around this value that the manufacturer mentioned, but you don't know exactly what it is. So you're gonna like selectively choose different values around this to find the filter noise. Again, this is kind of an iterative practical problem that you'll have to do because it is super hard to determine the exact noise in your sensor. So you'll have to play around with it a little bit. But if you're having problems with that, you can always reach out to us, reach out to me. And if I'm not able to solve it, like we have like a whole bunch of engineers to help you figure this out. And Alicia, do we have any other questions?
We do. We've got a few. So,
Okay.
our engineer asked, he said, this webinar is about filtering sensor data. Would this filtering only be done after you have saved data from a system, or can this run live? And then added
Yeah.
some extra clarification saying live
Mhm.
meaning it's storing and filtering the data whilst the system is active, like measuring data from a drone in the air.
Yeah. It can, so you need the data to design the filters because you need to analyze and do it. But you can do it live, like I just showed here. So I am reading the data live and then filtering it, which is what this graph was, if you see here. Oh, it doesn't want to play again. What I can run it again for you. But what it shows is that you can read sensor data directly and then filter it real time. So you don't need to collect data and then filter it. It can do it in real time. So to run it again, I need to clear the IMU. So again, I'm clearing the IMU because in the last section, I set the samples per read to 1, so I can do like one sample at a time. But I'm going to change it to like 150 again, so that it is easier to filter the and IMU. So I'm going to clear these objects that I define, and once it's done, I can run it again and show you. And what's the next question, Alicia? I'll come back to this once it's done. Oh, I think I might have knocked loose one of the wires. Um, like I said, I do have a flimsy setup, so apologies for that. But we can take the next question, Alicia. I'll come back to this
Yeah. Yeah, so CJ asked a couple questions. The
one.
first one was getting spikes in our pressure sensor data when testing in a pool with surface chop and people moving.
Hmm.
Any thoughts on filtering transient noise in MATLAB without over smoothing the signal?
Right. So again, it's a fine line between over smoothing and filtering, which is something you'll have to play with. So the best approach would be having your sensor in this environment that you just talked about, like the people and like the spikes, and collect the data and analyze it and see where the noise is. So if you go back to the FFT, um, go back to the messy one. So the transient noise is a little harder to detect, but you can, uh, what you would do is have the IMU or like have your pressure sensor and collect data without any disturbance. Just keep it in an isolated environment and collect the data, and then collect data in the pool that you'll be deploying in, and then analyze what's the difference between them. So you can see there's like difference here, but in your case, it'll look different. And then that would determine where you want to design like which frequencies you want to cut off and which ones you want to keep. And again, the smoothing, it depends. If you like cut it too close to the source, if this is your actual signal value, and if you cut it to like 1 hertz, then it's going to be super smooth, but then you're losing a ton of actual signal, right? So you want to give it some buffer because there is some noise, so there is some signal within the noise range too. So that is something that you'll have to again iteratively try. So, but it's pretty easy to try different things because you just change values over here and then it would give you the filter to try them. Let me see if it was cleared. Okay, so I'm gonna go back to the previous question and then show them how you can filter live data. Let me run this again. So here I've read the samples for read to 150, so that's why I'm clearing and defining it again. Okay, if I go back all the way down. Yeah, so in the filter live data section, I will run this to show you. Um, well, okay, so it is doing the same thing that it did in the beginning of the webinar, but it should be okay now. Yeah, so now I'm moving the sensor like in real time, and it is filtering it based on like the filter that we designed. So you can do like real-time filtering with this one, but like I said, there's going to be a little bit of phase difference that hopefully would not be a problem. If it, I mean, for 99% of the cases, it won't be a problem. It's going to be super small, like here. Any other questions?
We have one more right now.
Hmm.
Another one from CJ who said this is helping right now. So thank you, Abhishek, for doing this for us. I know
Of
it's
course.
going to help all the students on this call, but ton of you guys
Hmm.
afterwards, if you're watching later. But he said we're seeing yaw drift without reliable magnum magnet. I'm gonna
Magnetometry.
thank you.
Yeah.
What filtering methods in MATLAB help estimate orientation accurately in this case?
So like I said, the IMU filter is pretty good. But let me open the doc page and show you. We have something. It's in a different screen. So the IMU filter is going to give you orientation from accelerometer and gyroscope readings. But if you scroll down, so we have like extensive documentation in all of these. Um, but if you go to the AHRS filter, that's the name. I forgot the name. So it's gonna fuse accelerometer, gyroscope, and magnetometer readings to get you orientation. So this is a little bit more robust because you have more input. Again, if your magnetometer reading is not um, accurate, you might want to look into different kinds of IMU as well. There are like different bunch of options that you can choose from. Obviously, the more expensive you go, there's going to be less noise in the system, and it's going to be more robust. But some of the low cost IMUs tend to have more drift, which is hard to like reduce if your inherent readings are itself super noisy. So depending on your budget or something, I would recommend to look at higher level IMUs. But also, if you're constrained by budget, you can still do an AHRS filter to like reduce the noise, but you might have to like play around with all these parameters, like the noise in your system to get like a more robust output. But again, since these are like specific examples, you can like send me an email with the problem that you are facing specifically, and I can get back to you with the like more detailed answers for that problem. You can also reach out to me in Discord. I'm there in the RoboNation server, so you can like tag me, and I think my name is just Abhishek Shankar in that one. But you can tag me, and I'll get back to you. So anything that works for you.
Those are all the questions we have.
Awesome. And I also think we are at time. Switch back to the presentation again quickly. Um, so yeah, in this webinar, we collected data. We designed a filter using the Filter Designer app or the live task. And then you were able to filter your signal to minimize noise. And then this is like a specific example, but this low pass filtering is useful for like other kind of sensors too, um, especially like a hydrophone, which is often used in RoboSub and RoboBook. Uh, I know you guys already had like a bunch of questions, but if you have anything more, you can always email to the email ID that is there in the chat, or you can reach out to me in Discord if you're in the RoboNation Discord server. But before I end up, I also want to quickly talk about RoboSub because that's coming up quickly. And we have a MathWorks award for RoboSub, which we're excited to have this year because we did it for Robot X last year and then we got some great responses and people really appreciated it. So we're going to do the same thing for RoboSub. So if you're using MATLAB or Simulink or Stateflow or any of our software for your for your submarine design, um, do make sure that you check it out. I think Alicia has already sent out emails, and you can also reach out to me for more questions regarding that. But we just want to know how you're using any of our software tools and if it was able to help you in solving your problem. And we have cash prizes worth $2,000. So make sure you check it out. And if you're using MATLAB, I would highly encourage you to participate.
Thank you so much, Abhishek. Echoing some of our comments here, this has been
Mhm.
extremely helpful, and I know many of our students have enjoyed it. Like he said, we're excited to be doing a MathWorks award for our RoboSub competitors this year. If you
Mhm.
aren't already planning RoboSubbers on joining us on Thursday, make sure you do. We've got our team time, our next team time for the year, and we can't wait to
Oh,
see.
that's this Thursday.
Yeah, that is this Thursday, 7 p.m., same time. We can't wait to see
Awesome.
you then, but also
Mhm.
later this year as we head to Irvine for the competition. But again, if you guys aren't with RoboSub, or even if you are and you're excited for our next MathWorks mini series session, we'll be back here on YouTube, 7 p.m. at May 6th. We're going to be talking about designing and deploying state machines with Stateflow. So we're really excited to have you guys here. And thanks once again to Abhishek from MathWorks. Like you said, if you've got questions, feel free to send an email to the account that he has in the chat, as well as feel free to check out all the links in our description and reach out to RoboNation as well. If you've got questions, we'll pop our email in the chat chat as well, humans@robonation.org. Thank you so much.
Thank you.